Hello everyone, I'm Peng. I'm a research assistant at Academia Sinica, Taiwan. Today I'm excited to present our work. Pixel is not a barrier, an effective evasion attack for pixel domain diffusion models. With the rapid advancement of diffusion models, such as Stable Diffusion, users can now generate photorealistic images effortlessly. A subsequent work, ControlNet, enables more nuanced control over the generations. Diffusion models also allow for the easy conversion of images to noisy data for manipulations. Chen et al. Proposed SD-Edit, a general editing framework that enables various downstream editing tasks and becomes a fundamental method in diffusion-based image editing. This method allows for diverse editing capabilities such as image compositing, image translations, and even face swappings. While these advancements have revolutionized creative workflows, they also introduce significant risks. For example, malicious actors can use diffusion models to manipulate images, alter sensitive content, infringe intellectual properties, or even create fake identities, which can aggravate the dissemination of misinformation. So how to protect our image against diffusion-based editing? We can approach this goal as an adversarial attack to the diffusion models. Our method, ATK-PDM, will add subtle perturbation on the image as a protection. And when performing SD-Edit, the edited result will be corrupted. Since SD-Edit serves as a cornerstone of many editing pipelines, by disrupting SD-Edit, our approach achieves a general solution across various diffusion-based applications. Here we focus on pixel domain SD-Edit scenarios, and we will explain the reason in the following slides. But before that, let's talk about the research gap with previous works. PhotoGuard proposed two attack methods targeting different parts of latent diffusion models. The first is to attack the diffusion process as a whole. However, this requires substantial memory usage, which even the most decent GPUs can hardly accommodate. Another work, Deep Protect, addressed the memory burden by score distillation, but finds that the attacking effectiveness is mainly attributed to the vulnerability of VAE encoders in the LDMs, and the diffusion process is still robust. Subsequent work also empirically found that pixel domain diffusion models are robust to previous attacking methods, and can even be a good purifier for LDM attacks. So this raises a critical question. Can we design an effective attack on the diffusion process that applies universally to both PDMS and LDMS without relying on the vulnerability of the VAE encoder or requiring a costly propagation through every diffusion step? So here's a reason why we choose to target pixel domain diffusion models, as they don't have vulnerable VAEs to exploit. In this work, we answer that question by proposing a novel attack framework targeting SD-Edit process. The problem formulation is to maximize the SD-Edit results under the same settings, while imposing a constraint to regularize adversarial image fidelity. Here's a conceptual illustration. First, we will add noise to both of the original image and the adversarial image with arbitrary time state t. Then we apply denoising models to calculate our proposed attacking loss to update the adversarial image, where we also calculate the fidelity loss to regularize the adversarial image quality. Here's our constraint optimization formulation as a surrogate to the problem. We will discuss the details of our proposed losses and tricks. After n steps of constraint optimization, we can successfully destroy the SD-Edit process. Now, let's dive into our proposed method. We will add initial perturbation to the original image to create an adversarial image, and do one-time initialization using a victim model agnostic VAE encoder for latent optimization. We then add noise to a certain noise label described by T feed into the denoising unit, and extract the feature representation in the middle layer. Here we assume the representation follows Gaussian distributions, and we calculate a certain distance to capture the feature representation discrepancy. This gradient is used to update the latency. And we also calculate the fidelity loss in the pixel space and use to update the latency. Since this is a constraint optimization problem, we incorporate an alternating latent optimization to solve it. Let's look at the example. In a normal SD-edit process, the feature representations of the input images are consistent with the original image. However, when we introduce adversarial perturbations, the feature representations are distorted, leading to corrupted editing results. We qualitatively compare with previous methods, and our method achieves better imperceptibility, while also having better attacking effectiveness. Our quantitative comparison characterizes two objectives. We want adversarial image quality to be good, while the edited image to be corrupted, as reflected by the same image quality matrix, but in totally different directions. Note that in attacking effectiveness matrix, we add image alignment score utilizing clip model to assess semantical deviations from expected editing results. The lower alignment score suggests higher deviation, which reflects a more successful attack. Compared to previous method, our approach achieves superior results in both adversarial image quality and attacking effectiveness. We also compare our method with the previous state-of-the-art method on conditional PDM default IF. Although the attacking effectiveness of previous SOTA seems better, this might be due to the projected image quality has already corrupted. Previous works point out that their adversarial perturbation is fragile to defense methods. We also evaluate our framework against various defense mechanisms, including the most powerful purification to LDMS. Unlike previous methods, our attack remains robust, maintaining effectiveness after defense. Additionally, our approach demonstrates strong transferability across bypass settings. We do an ablation study with different losses in our optimization strategy to demonstrate our method's superiority. Semantic loss is a noise prediction MSE mainly used in previous works. Here we can see when incorporating semantic loss, the perturbation is significant, but attacking effectiveness is insignificant. Semantic loss combined with our latent optimization strategy can make the perturbation smoother, but attacking effectiveness is still insignificant. Adding image fidelity loss as a regularization further improves the adversarial image quality, but the attacking effectiveness is again insignificant. Incorporating our proposed feature attacking loss and fidelity loss, the attacking effectiveness is significant, but the adversarial image quality is impractical to use. So we show that combining our latent optimization and attacking loss can significantly enhance both of the adversarial image quality and attacking effectiveness, making it suitable for real-world scenarios. Here's the takeaway. Although the denoising process of PDMS and LDMS seem robust, there still exist vulnerabilities in the feature space inherent in the denoising models. Our method shows the denoising process of the PDMS are robust to pixel-level adversarial perturbation, but susceptible to perceptual-level adversarial perturbation. We can perform optimization of the latent space of a victim model agnostic variational autoencoder to create an effective perceptual-level adversarial perturbation against PDM while maintaining the image fidelity. Thanks for your attention. Please feel free to check out our project page for a full paper and implementation details.